back. Today I want to take a look at deriving the formula for the time period of a pendulum in terms of the pendulum's length. Okay, so how fast the pendulum will swing or its angular velocity depends on the length of the pendulum, but we're going to look at how that is the case. So let's start by drawing a simple pendulum. Okay, as a pendulum is swung from its equilibrium position here and it's swung out to the right, and we'll call the right positive direction. Okay, the pendulum has a length L and it's swung out an angle theta, and using simple trigonometry you can see that side there will be L sine theta, but for now we're just going to call it X. Okay, positive X, and when it swings out this way that's going to be minus X. Okay, now if I allowed that pendulum to swing and I plotted the position, well, when it's at maximum positive position it's going to be there, then it's going to travel back to the center, that means it will be here, and then it's going to go out to the full extent to the left, so that's negative displacement, and then it's going to return back to the center and go back to where it started. Okay, and from your maths lessons you should see that maps out a cosine function, and that's exactly what we're going to call it. Okay, so from that I can write, let's change color, that the position of X is equal to basically cosine omega t. Now, where does the t come from? Well, if this axis is time and this is position, you can see we get X equals cos t. So what about this omega? Where does that come from? Well, let's just have a quick look at that. We know from our A-level physics classes that omega, or lowercase omega, the Greek letter, is angular velocity, right? So what does that mean? Well, it means theta radians per some unit of time. Okay, if I just rearrange this equation, I can see theta equals omega t. Okay, so when you see cos omega t, it's basically just an angle. Okay, it's an angle, but it's in terms of time, which is quite useful for when we're talking about simple harmonic motion. Now, a bit more information on little omega. If it does one full circle or 2 pi radians in some amount of time, capital T, we've now got angular velocity in terms of the time period, right? That's radians per second. But we know frequency equals 1 over t. So we could also write this as 2 pi f and see that the angular velocity omega is some function of frequency. Okay, so it's all tied in together: time periods, frequencies, angular velocity. Remember, angular velocity is distinct from what we would call tangential velocity, and that's related by the equation v equals omega r. Okay, so that your tangential velocity would increase the further out you go from the center of rotation. That's what that means. But what we're concerned about is angular velocity is a function of frequency. So let's go back to our formula. So we now know omega t is an angle, so x equals cos theta or cos omega t. Omega acts as the frequency component. Okay, so if I increase the angular velocity, i.e. my pendulum swings faster, yeah, it swings from one side to the other and back again in less time, i.e. it's going faster, that would increase the frequency component of the sine wave. Okay, now what can I do next? Well, if anyone's done the A-level maths, you should know if I take the derivative of position with respect to time, so if I did dx over dt, this actually equals velocity, okay? So I can calculate the velocity of the pendulum at any position. And what I need to do is differentiate the cosine, and the derivative of cos is minus sine. And using the chain rule, I'm going to get omega pops out to the front. So I'm going to have minus omega sine omega t. Okay, and that will give me the velocity at any time within the pendulum's action. Alright, so we've gone from the displacement to the velocity, and I want to do one more differentiation. I'm going to derive v, so if I do the derivative of velocity with respect to time, that gives me acceleration. And it's the same again. What's the derivative of sine? Well, that's cosine. So I'm going to have minus, the omega comes out again using the chain rule, omega squared cos omega t. Okay, so acceleration equals minus omega squared cos omega t. Now, earlier we said that cos omega t equals x. So I'm just going to do one little final manipulation here, and I'm going to say acceleration equals simply minus omega squared times x, okay? And this is an important equation because that is the basic definition of any object in undergoing simple harmonic motion. Okay, very important. The acceleration of the object is proportional to its distance from the equilibrium, i.e., so if x is 0 or the pendulum's in the central position, it will have no acceleration. And it's also proportional to how the angular velocity, or how many cycles per second this object is doing, the time period. Okay, so that's good. We've just defined the basic equation of simple harmonic motion. What can I do next? Well, I want to apply this to to the case of a pendulum. So what I'm going to do, I'm going to rearrange it or do some substitutions. And instead of minus omega squared, I'm going to replace that with 2 pi over time period. So we get time period involved. So let's do some rewriting. Acceleration equals. Now minus, I'm going to drop the minus out, okay? We'll just have to remember ourselves about the minus. But omega, I just said before, it was the same as 2 pi over the time period, all squared, times x. Okay, and I'm going to multiply through by that square term, and I'm going to make t squared the subject of the equation, okay? So let me do that now. Change colour. T squared equals, well, what does it equal? It's going to be, if I multiply through by the square, I'm going to get 4 pi squared x all over a. Okay, so this has given me the time period of something in simple harmonic motion. The next bit is I'm going to square root both sides, so that 4 pi squared is going to become 2 pi, and then I'm going to have the square root of x over a. So I'll just do that next. Square root both sides, so I get t equals 2 pi x over a, and all that's square rooted. Okay, brilliant. So for any object in simple harmonic motion, I can work out the time period given this equation here. Now, what I need to do is find the x in a in terms of the length of the pendulum. So what I'm going to do is go ahead and do that now, but I'm going to do that by doing another little sketch up here. Okay, I'll start up there. Okay, so another pendulum here with length L, angle theta. So this side with X position will be L sine theta. Okay, so the X of that equation before is L sine theta. Now, let's think about the force. Let's think about the force on the end of the pendulum. If this is the end of the pendulum there, it's going to have mg, its own weight, pulling it down. Now, not all of that force or the weight is going to be acting in the direction of the object's travel. Now, as the pendulum goes to the furthest right position, or its furthest positive displacement, all of its weight is going to be wanting to pull it back in this direction. Right, I'm going to resolve that vector. That's a right angle. This angle will be theta. So the force pulling it back here, this force is mg sine theta. Okay, using simple trig, that's the force pulling it back. Now, I want the acceleration for that formula. It was the square root of x over a. I've got x, that was L sine theta, but I need to just do a bit of rearranging of Newton's second equation, which is, he said F equals ma, didn't he? So that means if I rearrange that, I can get A equals F over m. And I just worked out F, didn't I, just now? So A equals F, which I said was mg sine theta. That's the only force acting in the direction of the pendulum's motion. And over m, and I can see the m's cancel. So acceleration equals g sine theta. Okay, and the x, if I zoom out a bit, I could see that the x component was L sine theta and A is g sine theta. So I can go ahead and go back down to my formula here. And substitute there and there. So I'll go right ahead and do that. And I'm going to end up with t equals 2 pi. X was L sine theta. A was g sine theta. All that was square root. The sine thetas cancel. And finally, we're left with a beautiful equation. Let's make it in black. T equals 2 pi L over G square rooted. So you can see, if I zoom out, see all of that work. The time period is related to merely the length of the pendulum and the gravity of the planet, or, the value of G in whichever gravitational field you're in. So if you took your pendulum to Jupiter, G would be larger. That would make the time period smaller, i.e. the pendulum would oscillate more quickly. If you increase the length of the pendulum, you're going to increase the time period, which means the pendulum will swing more slowly. So I hope that gives you an idea of like an overview of simple harmonic motion, how we can apply the basics of that to a pendulum, and how we can derive the formula for the time period of a pendulum. Okay, thanks for watching. See you later.